All right, this will be an overview for exam 4, kind of what we're covering. But it'll also help with quiz 4 since it's like the first 3/4 of this. So the very first things we want to cover were pieces from the previous chapter, which is chapter 3 and L'Hopital's rule. So what I want to do is I want to evaluate some limits using L'Hopital's rule. So first, let's say let's do the limit as x goes to say 4 of x squared minus 16 all over x minus 4. Now this is a classic one that you would see in like the first set of limits, because you do this simply by factoring. This is x plus 4 times x minus 4. The x minus 4s will cancel, so this thing will simplify to x plus 4. When you plug in 4 plus 4 is going to be 8. So we already know its limit's 8, but when we do L'Hopital's rule, what it says is you take the derivative of the top over the derivative of the bottom. Now remember, this is not the quotient rule. This is just how we evaluate limits using L'Hopital's rule. So L'Hopital's rule says you take the derivative of the top, which is going to be 2x, all over the derivative of the bottom, which is just going to be 1. And I did fail to mention that L'Hopital's rule only works if you have an indeterminate form of like 0 over 0 or infinity over infinity. So, when you plug in 4, you get 0 on top. When you plug in 4, you get 0 on bottom. So if you were to evaluate it, you would see 0 over 0, which is indeterminate form, which means you don't really know its answer. You have to do some, simplification, or you can use this trick, which is L'Hopital's rule. So derivative of the top is 2x, derivative of the bottom is 1. Notice now this is no longer 0 over 0. When you plug in 4, this is 8. When you plug in 4 on the bottom, this is 1. So we're done. There's no more L'Hopital's rule because it's now simplified. So 2x over 1 is just 2x. So this is just going to be 2, plug in x is equal to 4, so we get over 1, but which is going to be 8. Now, L'Hopital's rule can be repeated, multiple times. So say the limit as x goes to infinity of, let's say 5x squared minus 4x plus 1, all over, say, x squared plus 7. So what we can see is if I was to try to evaluate this at infinity, the top will be infinity, the bottom would be infinity. And the previous way we used to do this is we would multiply top and bottom by 1 over x squared, because that's the highest power that we see. So, this is simple at 5. This would be negative 4 over x. This would be 1 over x squared. This would be 1. This would be 7 over x squared. And when you take the limit as x goes to infinity, those terms will cancel. So then you're just going to get, 5 over 1. Now, L'Hopital's rule, works for this as well, because it's indeterminate form. We have infinity over infinity, so we just take the derivative of the top, the numerator, over the derivative of the denominator. So this is going to be 10x minus 4 all over 2x. Now, previously it was done because you no longer had indeterminate form, but, if you plug in infinity, the top is still infinity, the bottom is still infinity, so this is still indeterminate form, so we just repeat the process. So derivative of the top being 10, the derivative of the bottom being 2. So this is going to be 10 over 2. And I can even evaluate at infinity. The limit of a constant is just the constant itself, so 10 over 2 is equal to 5. The exact same answer that we would have got, if you're back in, chapter 2. All right. Let's do another one. So if I plug in 0, this would be 0, this would be 0, this would be 0. So I have 0 over 0. So this is indeterminate form, which means we can do L'Hopital's rule. So the limit as x approaches 0, the derivative of the top is going to be 1 minus cosine of x, all over the derivative of the bottom, which is 3x squared. Note that, again, this is not the derivative of this thing. This is just a way we can handle limits using L'Hopital's rule, the derivative of the top over the derivative of the bottom. If you're going to take the derivative of a quotient, you would actually need a quotient rule. All right, so let's see what happens when we plug in 0. Well, this would be 1. This will be 1, so the numerator is 0. When I plug in bottom, the bottom would be 0 as well. So this is still 0 over 0, which is indeterminate form. So again, we just repeat the process until it's no longer indeterminate form. So x goes to 0. Derivative of 1 is 0. Derivative of negative cosine would be minus sine. So minus and minus sine is going to be sine of x. all over 6x. And then we see if I can plug it in yet. Well, plug it in, the sign of 0 is going to be 0 on the bottom. 6 times 0 is still 0. Still a determinate form. So just repeat until this is no longer 0 over 0 over infinity or infinity. So limit as x goes to 0 of derivative of sine of x is cosine of x. The derivative of 6 is going to be 6. So let's see what happens now. Well, when you plug in the cosine of 0, you get 1. And the bottom is 6. So this is no longer a determinate form. So this is going to be plug in 0, you get 1. Plug in 0, you get 6 on the bottom. So this is our answer, 1/6. Now there's another kind of problem that I put on every quiz and every test, and this is I throw some logarithms in there just so we know how to simplify our logarithms, just using a particular property. So let's say x goes to 0 of, say, the natural log of, let's say x minus the natural log, that's not natural log, minus the, say, x squared, minus the natural log of x squared plus 3. All right, so I do this because, in order to do L'Hopital's rule, it has to be in, a quotient form. It has to be 0 over 0 over infinity over infinity. Right now, this is a subtraction. So it doesn't work for subtractions, but I know for the rules of logarithms, the difference of a logarithm is the logarithm of the quotient. So this is equal to the limit as x goes to 0 of the natural log of the numerator over the denominator. What we're doing is this property here. The natural log of a minus the natural log of b is equal to the natural log of a divided by b. That pre-calculus rule. So, this being a, this being b, so this becomes the natural log of a over b. Now what it allows us to do is, now this is the natural log of a quotient, and I know with logarithms that you can apply the logarithm to the inside because the natural log is a continuous function. So this is equal to the natural log of the limit as x goes to 0 of x squared all over x squared plus 3. So now I can just kind of ignore this natural log for a little bit and work just in the inside. So this is a quotient, 0 over 0, so do L'Hopital's rule. So the natural log of the limit as x goes to 0 of 2x all over, 2x again. I know you can simplify that to 1, or you can repeat it again because it's technically 0 over 0. But so you're going to get 2 over 2 or 1 regardless of this. So this is going to be the limit as x goes to 0 of 1, and the limit of a constant is that constant. So this is the natural log of 1. And if you guys remember your values of logarithms, the natural log of 1 is equal to 0. So this will just be equal to 0. If you remember a logarithm, it looks like this, right? So the natural log of 1 gives you an output of 0. That's why you get 0 there. But I always put this on every test and every quiz where you have to take the difference and put it into a quotient. So that's your basics of L'Hopital's rule. They, of course, you can get messier and messier, but they're very similar to that. So the last part of this chapter goes into just finding the general antiderivative, which I find it interesting that they put in chapter 4, when really I think it probably could be the introduction to chapter 5. But they do it in such a way as the antiderivative being the reverse of the derivative. So it's fair. I can live with their locations. But really, we're using this this antiderivative for really the rest of class, and how antiderivatives pertain to areas. So if I want to find, say, the most general antiderivative, so example, find most general antiderivative. A could be, say, the integral of 3x to the 4th plus 2x cubed minus x squared plus x. Let's do like a 5x plus 1. There. So all the way up to a fourth degree. So what we know is when we're working with polynomials that the antiderivative of x to the n dx is equal to x to the n plus 1 all over n plus 1 plus c. So you add 1 to the power, then you divide by that same power. So remember that constants, just like derivatives, can be pulled out. So this is going to be equal to pull out that 3. Now I have x to the 4th, so n is 4. So this is going to be 4 plus 1, which should be 5 over 5. So this would be x to the 5th, over 5. Plus, again, pull out the constant. Now add 1 to the power, divide by that same number. So this is going to be x to the 4th over 4 minus x cubed over 3 plus 5x minus 1 right now. So it's going to be squared over 2 plus, this technically is x to the 0 if that helps. So this is just going to be x plus c. And then we can kind of go back. The derivative of x is equal to 1. The derivative of this would give me 2 times 5, which would be 10, divided by 2, which would be 5x to the 1. So it's going to be this. So know that the derivative of this is equal to this thing. When we say most general, that's why we're basically saying the plus c, because the derivative of a constant will always give us the 0 back. Other ones I always put on there is just, practicing, what happens when you have radicals. So like the square root of x minus, say, 5 over root x dx. Oops, gotta write a dx here. It's funny. It's the integral with respect to x. That's why we like that. All right, so in order to take its antiderivative, I know that these things have, these coefficient variable power notations. So, this is the same thing as the integral of 1x to the 1/2 minus, well, this is 5 over 1, so 5x to the negative 1/2 dx. And now something that looks messy now becomes very similar to this. So we apply the same thing, x is a half. So 1/2 plus 1 is going to be 3/2 all over that 3/2. So this is going to be x to the 3/2 divided by 3/2 minus, pull out the constant, add 1 to this. So negative 1/2 plus 1 is going to be positive 1/2 all over 1/2 plus c. Now this is the correct answer, but remember we're in calculus class. We can simplify a little bit. So divided by 3/2 is the same thing as multiplying by 2/3. So this is going to be 2/3 x to the 3/2. Divided by 1/2 is the same thing as multiplying by 2. So minus 10 x to the 1/2 plus c. And if you want to rewrite this as root x, that's fine too. But I really just want to make sure that you don't have complex fractions in here. Like a fraction over a fraction. So only one fraction bar per term. Okay, so then we get into products and quotients, and this is just to really reinforce the fact that what's nice about derivatives is there are product rules, there are quotient rules. What's not nice about antiderivatives is there are not product rules and quotient rules. We'll eventually get to things that'll handle something similar to that, but they're not nearly as nice as derivatives. So when it comes to derivatives, your first thing really you have to do, or antiderivatives, is simplify first, take the antiderivative second. So there is no rule for products, so what we're going to do is we're going to multiply first, take the antiderivative second. So I'm going to FOIL this. So this is the integral of x times x squared times x is x cubed. Outside is going to be plus 4x squared. Inside is minus 3x, and then last is 12 dx. And now it looks something very similar to, number 8. It's just the antiderivative of a polynomial. And then we get to use, antiderivative of the polynomial rule, or a power term rule. So this is going to be equal to x to the fourth over 4 plus 4 times x cubed over 3 minus 3 times x squared over 2 minus 12x, and don't forget our plus c. Does anything simplify? No, we're good. So that's it. So then the last one would be, say, well, not really the last, but what about, say, the antiderivative of a quotient? If I have, like, how messy do I want to make this? Let's say 4x minus x cubed all over x squared dx. All right. So, again, there's no rules for quotients, so what we're going to do is we're going to simplify first and then take the antiderivative second. So the monomial denominator is a dead giveaway that you're just going to split this thing. That this is, they're both being divided by x squared. If the bottom's a binomial, then that's a little bit different because you're going to have this over a binomial, this over a binomial. But this being a monomial means I'm going to be able to simplify each one of these terms. So the integral of 4x all over x squared minus x cubed all over x squared dx. This is very similar to what we were doing with derivatives. Like sometimes you can simplify first and take the derivative second. So with antiderivatives, you always want to simplify first. Make it easier because antiderivatives are more complicated. So now, one of the x's cancel here and then two of the x's cancel here. So this is going to be the antiderivative of 4 over x, or 4 times 1 over x minus x dx. Now, if you guys remember that 4 over x is the same thing as the antiderivative of 4 times 1 over x dx. So we know the derivative of the natural log of x is 1 over x. So the antiderivative of 1 over x is going to be the natural log of x. So that's just stuff you have to recognize, just like with logarithms. So this is going to be 4 times the natural log of x. So this will be 4 natural log of x, and you can check it. If I took the derivative of this, I better get this thing back, since this is the antiderivative. So the derivative of the natural log of x is 1 over x times 4 is going to be 4 over x. And the antiderivative of this is going to be, x squared over 2 plus c. Then we have polynomials and, our favorite inverse trig function. And maybe a couple exponential functions. So how about let's see, this is going to be the e. How about the antiderivative of e to the 3x plus the cosine of 2x. What else do I want? Let's say plus the secant squared of x dx. There, that's a good one. All right. So for this one, there's a rule here. This is the antiderivative of e to the, what do they write there? I'm just going to say bx dx is going to be 1 over b e to the bx plus c. Or they say e to the bx over b plus c. So the way I try to memorize, say, this rule here is if we were taking the derivative of, say, if I was going to ask for the derivative with respect to x of e to the 4x dx, for instance. That's stupid. Let me try that again. My bad. There we go. If I was going to take the derivative of this thing, what I know is it would be itself, but then I'd have to multiply by the derivative of the inside, which is a chain rule, so the derivative of 4x is going to be 4. So with derivatives, you have to multiply by the inside. But with antiderivatives, you're going to have to divide by that inside. So if I took the derivative, I'd have to multiply by b. It'd be e to the bx times b. But if taking the antiderivative, it's going to be e to the bx divided by b. So antiderivatives work in the reverse direction as derivatives. So just kind of knowing that it's got to be the reverse of this idea here. So the antiderivative of this is going to be e to the 3x divided by 3. Or 1/30 to the 3x, whatever you want to write. This is very similar. if I was going to take the derivative of, say, the sine of 2x or the cosine of 2x, you take the derivative of that function, but then you'd have to multiply by the derivative of what's inside, so you'd have to multiply by that 2 there. So just like with exponentials, you do the same thing for trig functions. So what function do you take the derivative of to get a cosine? Well, it'll be a sine function. So this is the derivative of a sine function. So this is going to be plus, well, the sine of 2x, because the derivative of the sine of 2x would give you the cosine of 2x. But then you would have to multiply by that 2. This doesn't have a 2 here, so I'm going to have to divide by that 2, so 1/2. Or I could say over 2, so we can write it, this way, very similarly. 1/30 to the 3x plus 1/2 sine of 2x. So don't forget, just like this idea here, that you have to divide by that constant, because there's just a 1 here. And you can double check that. The derivative of the sine of 2x is the cosine of 2x times 2. So 1/2 times that 2 is just going to be a 1. And what function do you take the derivative of to get a secant squared? Well, the derivative of the tangent is secant squared of x. So plus the tangent of x plus c. So the derivative of the tangent is secant squared. And then we're done. It's really just kind of knowing how to handle these things for exponentials and trig functions, and just kind of remembering the antiderivative of certain trig functions that we've become very familiar with over the last 10 weeks. F. One last one. Let's say the antiderivative of 1 over 1 plus x squared dx. This is just a recognized rule that if you've seen this is the derivative of a particular thing, and this happens to be the derivative of our tangent inverse function. So the derivative of this is equal to this. So the antiderivative of this is equal to this, of course, plus c. What followed this general antiderivative was came to something called initial value problems, which really is kind of like your first look at what we consider differential equations. So solving the initial value problem was really asking you to find the function for which this thing is true. So let's say solve the initial value problem. So let's say the derivative of y with respect to x is equal to let's say 3x squared minus 4. Let's say something like that. But I have to give it a condition, so I know that, let's say y of 0 is equal to, let's say 5. All right, so in order to solve this initial value problem, what I'm really asking you for is I'm asking you for the function y, or y equals f of x. So what we're asking for is, what is the function so that I take its derivative, I get this thing back. That's really my goal here, is what function do I take its derivative, what function to where this is equal to this. So, if I take the derivative with respect to x of this, I know it's going to be that thing. So another way of asking that is really, what's the antiderivative of this? So, y is going to be equal to the antiderivative of 3x squared minus 4dx. It's going to be the reverse of the derivative. So the antiderivative of 3x squared is going to be x cubed over 3, so those 3's will cancel, so this is going to be x cubed. And the antiderivative of 4 is minus 4x plus c. Now that's my function, but there's one more stipulation. I need to know this thing has to go through the point 0, 5. This thing has to have a solution of 0, 5. So when I plug in x equals 0, when I plug in x equals 0, y better be equal to 5. So 5 is going to be 0 cubed minus 4 times 0 plus c. So you can see that 5 will be equal to c. So therefore, our solution to this is y is going to be equal to x cubed minus 4x plus 5. So I know that the derivative of this is equal to this, and this function goes to the point 0, 5. Now we can have another one to where, let's say, I give you a second derivative and you might have to do it twice. So let's say its second derivative with respect to x is going to be equal to, let's say, 4x squared minus 3. I don't like that. Let me say, let's do this. I don't want it to be super messy. So let's say 9x squared minus 2. Yeah, I like it. Okay, so, but I have to give a couple initial conditions. So we're going to say that where y of 0 is equal to 1 and y prime of 0 is equal to negative, I don't know, 4. All right, so again, what I'm trying to find is I'm trying to find the function y. What does y equal? Well, I didn't give you guys y. I gave you y double prime. This is the second derivative. So I need to find the original function. Well, I can't do it directly. I know that I can find y prime, which is the same thing as dy dx, simply by taking the antiderivative of the second derivative. So this is going to be the antiderivative of this with respect to x. So, dy dx is going to be equal to 9x cubed over 3. 9x cubed over 3 minus 2x plus c. So this is, 3x cubed minus 2x plus c. So that's our y prime, right? Our y prime or dy dx. Now I know that dy dx has to go through 0, 4. So when I plug in x is equal to 0, y prime better be equal to 4. So, 4 is going to be equal to 3 times 0 cubed minus 2 times 0 plus c. So you can see c is equal to 4. So that means dy dx is this thing with c is equal to 4. All right. Now I don't want to know dy dx. I want to know the original function y. So again, what we do is we take the antiderivative of this. So y is going to be the antiderivative of 3x to the 4th minus 2x plus 4 dx. So the antiderivative is going to be 3x to the 4th over 4. So 3x to the 4th over 4 minus 2x squared over 2. So the 2's will cancel. Plus 4x plus c. So now this thing has to go through the point 0, 1. So when you plug in x is equal to 0, y better be equal to 1. So 1 would be equal to 3 times 0 to the 4th over 4. Those 2's will cancel. Minus 0 squared plus 4 times 0 plus c. So you can see that c is equal to 1. So finally my answer is going to be this thing with c is equal to 1. So y is equal to 3x to the 4th over 4 minus x squared plus 4x plus 1. So that'll be, I know that the second derivative of this thing will be equal to this. Its first derivative goes to this point, and this function goes to this point. Really, it's just a application of finding antiderivatives. Knowing that the antiderivative is the reverse of the derivative. That if I take the derivative 2 times, I'm going to get this. All right, so how does this antiderivative become useful for us? Well, a lot of times we use this for finding areas underneath curves. And then eventually when we get into like Calc 3, we can drop this into 3 dimensions and we can find volumes of surfaces. Very interesting surfaces. Surfaces that might just not have this pretty geometric formula. Or maybe we can prove the formulas of why, a cylinder is pi r squared h and stuff like that. Like where do these formulas come from? So, but we have to start first. We're going to have to work in 2 dimensions before we can move into multiple dimensions. So areas under curves can be described through, definite integrals, as we call that. As opposed to what I'm erasing now is we're using indefinite integrals because there are no limits of integration. So what I might ask you to do is determine, upper and lower sums. Let me write it this way. So given the function, let's say f of x is equal to, say, x squared plus 3 on the interval, say, from 0 to 2. Let's determine, let's say, I want the lower sum using, say, 4 rectangles. And then B will do the upper sum using 4 rectangles. Then we can actually find the true area, and then we can verify this with a definite integral. We'll kind of tie it all together. So what I know is that this function over here is x squared plus 3. So 1, 2, 3. It would look like this. It's, it's that quadratic function that looks like so. But I only care about this on the interval from, from 0 to 2. So just 0 to 2. I only care about it right there. So I'm just going to erase this part of it because it's not very, it's not useful to this picture. And what I want to do is I want to be able to find, the area underneath the curve of this thing, on this interval. So what I want to do is I want to cut this thing into 4 rectangles. So I know 0, 1, and 2, what values do I need to evaluate in order to do that? Well, the way we first start is we look for the change in x. So change in x is going to be b minus a over n being the number of rectangles, so that's 4. And a and b being the beginning and the end of your interval, so b being 2, a being 0. So this is going to be 2 over 4, which is a half. So what I'm going to do is I'm going to slice this thing into halves. So 0 plus a half is going to be a half plus a half is going to be 1, 1 plus a half is going to be 3 halves. So now what I'm going to do is I'm going to, in order to find the lower sum, I really kind of want to ask myself, what endpoint do I use? So we can see that on this interval from 0 to a half, I'm going to create a box here. I need to make sure that that box is below the curve. So the question is, do I use a left endpoint or do I use a right endpoint? Well, a left endpoint is going to send me this way, and a right endpoint is going to send me above this. You'll see in the next picture. So I can see that I'm using left endpoints. So similar here, I have another box, between 1 half and 1, I'm going to have to use that left endpoint. The 1 and 3 halves, I'm going to have to use that left endpoint. And finally, the 3 halves to the 2, I'm going to have to use that left endpoint. So you can see that these are the 4 evaluation points that I'm going to use. I'm going to use 0, I'm going to use a half, I'm going to use 1, and I'm going to use 3 halves. That's how I'm going to find the heights of these boxes, because I'm trying to find areas under the curve by a rectangle estimation. So what I notice is, our area is going to be equal to, I'm going to have f of 0 times, a half plus, what I'm doing is I'm doing height times width. So I know the width of each box is going to be a half. So each one of these are going to be multiplied by a half. So the first box is going to be, this is the height, which is 0. So f of 0 is going to be that height times a half, which is going to be that width. Plus we're going to have f of a half times, well, f of a half is going to be this height times this width, which is going to be a half. Plus now the next height, which is going to be f of 1 times a half plus f of 3 halves times a half. Or, what would probably be better, since I have a half multiplied every single time, I can really just go f of 0 plus f of 1 half plus f of 1 plus f of 3 halves, all multiplied by a half. All multiplied by a half. Just pull out that 1 half. So you just evaluate this function at each one of these points. Now, I was not really pleased with the fact that it chose a half for each one of these intervals, but I'm just going to evaluate these things and write these in fraction form. So, clear, let's see, x squared plus 3, table. No, let me do it this way. Second quiz. So, well, the easy one is when I plug in 0, this one's going to be 3. Plus, now when I plug in a half, well, a half squared is going to be a fourth. A fourth plus 3 is going to be 3 and a fourth. So 3 times 4 is 12, so this is going to be 11 fourths. Plus, when I plug in 1, this will be 1 plus 3, which is going to be 4. When I plug in 3 halves, well, that's going to be 9 fourths plus 3. 3 times 4 equals plus 2. We do this just to make sure I don't mess it up. Yep, 21/4 times half. Now adding all these values up and multiplying, I'm not even going to mess around those, so let's go. That was wrong anyway. Nice work. Simple math is hard sometimes. So 1/2 squared plus 3. Okay, so so now I got 3 plus 13 divided by 4 plus 4 plus 21 divided by 4 equals. So this is going to be equal to 31/2 times 1/2. So this is going to be equal to 31/4. Which will be approximately 7.75. Not approximately, it's exactly 7.75. If I want to find a lower sum, if I want to find an upper sum, if I want to find an eraser, if I want to find an upper sum, what we can do is very similarly, we are going to grab these things, but if I want to do that upper sum, do I have enough room? Not really. So if I want to do the upper sum, we're doing the same exact thing here, but at the exact same points because our change in x is identical. So if we want an upper sum here, notice that I'm going to be using right endpoints because I want these rectangles to be above the curve this time. It depends if the curve is increasing, if it's decreasing, if you're going to use right or endpoints. And it also depends if you want to do an upper or lower sum. So I can see that these are the evaluation points I'm going to use for the height now. And each one of these widths are still going to be a half. Now this is going to give me a little bigger value than the previous one. So now we're going to use 1/2, 1, 3/2, and 2 as our evaluation points. So just like this, except instead of these, we're going to do... I don't know if you guys noticed this, that this is the sum of f of x times your change in x. That's what this is, the addition of f of x times your change in x. So, well, from, well, I gotta be a little careful. I don't want to do integer points. I'll just leave it like that for now. So now we're going to have, f of 1/2 plus f of 1 plus f of 3/2 plus f of 2 all multiplied by half this time. So using those 4 points instead of those 4 points. So now a lot of these we already know the value for. Half is 13/4, 1 is 4, 3/2 is 21/4, and then 2 squared is 4 plus 3, which is going to be 7, all multiplied by half. And what do we get here? So 13 divided by 4 plus 4 plus 21 divided by 4 plus 7. So I get 39/2 times this half. So we're going to get 39/4, which would be exactly what? 39 divided by 4 is 9.75. So what I know is the true area is going to live somewhere between 7.75 and 9.75. If this was a straight line, it would live exactly between the two numbers, but this is a, this is a curve. So I'm going to write these over here. So I know A, we had 7.75, B, we had 9.75. What I want to do is I want to do this now the long way and find the exact answer using limits and an eraser if I can find it. Aha. All right. Don't do that. So 7.75 and 9.95. 75. I just want to refer back to those answers because I know the true answer is going to live between there, and I just want to prove that to you. All right. So C, what I want to do is I want to evaluate using this. We want to find the actual area using the limit as n goes to infinity of the summation from k equals 1 to n of f of c sub k times my change in x. So we were doing just integer values between here and here, but what I want to do is I want to do the limit as n goes to infinity. Instead of just like from 1 to 4, what we did now, I want to do something a little more fine. I want to do an infinite amount of rectangles instead of just 4 rectangles. And we're just going to do a lower sum because if you do an infinite amount of rectangles, your upper and lower sum actually converge to the same number. So just for convenience, we'll just do it as a lower sum instead. So what I've shown people is we know that our change in x is still b minus a over n. So this is going to be 2 minus 0 over n. Now, I'm using n rectangles, so we just have to leave it as n. When n was 4, this was a half, but we're going to take the limit as n goes to infinity. We're going to squish these things further and further and further. Now, your c sub k ends up being your change in x multiplied by k. So this ends up being k times your change in x. So what this is this is the arbitrary evaluation point that we used before. So previous, your change in x was 2 over 4, which is going to be 1/2. So when you do the lower sum, the first would be k would be 1 times a half, so it's a half. The second would be 2 times a half, which would be 1. The third would be 3 times a half, which would be 3 halves. And that's how we had those value points of 0, 1/2, 3 halves. Now this is going to be for, that arbitrary k value, since I'm taking an infinite amount of rectangles. So this is going to be k times 2 over n, or 2k over n. So remember last time n was equal to 4, and my lower sum, when k is 1, 2, 3, and 4, would give us those correct evaluation points. All right, so now what I'm going to do is I'm going to plug these things into here first, and we'll take the limit last. So we're just going to kind of simplify that expression. We'll take that limit at the very, very end. So this is going to be the summation from k equals 1 to n of f of 2k over n multiplied by the change in x, which is going to be 2 over n. Now, 2k over n is just acting as my variable x, so I'm going to plug it right in there. So this is going to be the summation from k equals 1 to n of 2k over n squared plus 3, and I still have to multiply by 2 over n. So what I'm going to do is I'm just going to work inside the parentheses. I'm going to simplify this as much as I can, and I'll multiply that 2 over n last. There's multiple ways to do this. This is just the way I have become accustomed to it. So summation from k equals 1 to n of squaring first is going to be 4k squared all over n squared plus 3 times 2 over n. And now I can distribute that 2 over n through. So this is going to be the summation from k equals 1 to n of 2 times 4k squared is going to be 8k squared all over n times n squared is going to be n cubed plus multiplying this by 2 over n is going to be 6 over n. Now, we have those couple summations, like the summation from k equals 1 to n of k is going to be equal to n times n plus 1 all over 2. The summation from k equals 1 to n of k squared is equal to n times n plus 1 times 2n plus 1 all over 6. And there's a k cubed, but we don't have a cube in here, so I'm not going to worry about that. And you also have the summation from k equals 1 to n of just the constant. It's just going to be n times c. So we're using those particular formula to be able to simplify these expressions in a second here. So what I want to do is I only want to have k's left over. So for this, the summation of a sum is the sum of the summation, so I'm going to summation both of these. For this one, I can pull the 8 over n cubed out, and I'll have the summation of k squared. K equals 1 to n. Plus, this is going to be the summation from k equals 1 to n of 6 over n. Now, I guess I could have pulled out the 6. I could have even pulled out the n if I wanted to as well. But notice that this term didn't have any k's in it. So since it didn't have any k's in it, it really looks like this one. So this 6 over n is nothing more than a constant. So that's why I didn't pull it out. But, for the other one, it looks like this. So that's why I wanted to pull that out. So that means I can replace, this piece right here with this expression right here. The n times 2n plus 1, you can see it. So this is going to be equal to 8 over n cubed, and this is going to be equal to n times n plus 1 times 2n plus 1 all over 6. Plus, now the summation of a constant is just going to be multiplying these two things together. You know, just the n times c. So n times 6 over n. And we can see that that's just going to spit out 6 in a second here. All right, simplifying. What I can see is that this n cubed is going to become n squared, and that'll cancel. So now multiplying inside here, this is going to be 8 times 2n cubed plus 3n plus 1. All I did is FOIL those two. All over 6n squared, plus, n. We're so close. I know it's messy. We're so close. So I can distribute this through. So this is going to be equal to 16n cubed plus 24n plus 8 all over 6n squared, and I still have that plus 6. So what that is that's a simplification of this thing here. The summation of f of c sub k times the change in x. What's interesting is if you plug in n equals 4 here, you'll get the exact same number. You'll get the 7.75 that we had before, because this is the general lower sum formula for n rectangles. So just previously, if n is equal to 4, if you plug in 4, you'll get the same answer. Now what I'm going to do is I don't want to use 4 rectangles. I want to use an infinite amount of rectangles. So I'm going to take the limit as n goes to infinity. So the limit as n goes to infinity of this expression, 16n cubed plus 24n plus 8n. Why does that not make sense? That should be an n squared. There we go. That's my bad. N squared. So all over 6n squared plus 8. I'm not going through L'Hopital's rule. We just talked about this. You can use L'Hopital's rule for this expression, and what I'll get is I'll get 16 over 6 plus 8. So this would be 16 over 6 plus 8. So, 8 over 3 plus 8. So what we're going to get is going to be 8 divided by 3 plus 8. So we're going to get 32 thirds. So what that ends up being is like 10.6. Ooh, shoot, that's not good. I don't like that. Oh, it's not plus 8, it's plus 6. Thank goodness. Okay. Ooh. So you already know what it's supposed to live between. It should be living between those two numbers. So let me fix that. Not plus but 8, but plus 6. So 8 divided by 3, enter, plus 6. Math fractions. So what I get is I get 26 thirds. That's better. Which ends up being 8.6 repeating, which does live between these two numbers here, as we kind of expected. So, this would be 8.6 repeating. Or 26 thirds is a much better number because you don't have a repeating decimal. That's why I like fractions better. They're more accurate. All right, the last thing I ask you to do is do this with a definite integral. So, part D. Evaluate using a definite integral. And what's beneficial about this is, oh my gosh, it makes this so much quicker, but it's cool. You're going to get the exact same thing that you see right here and here. So what I mean is that our area is equal to the integral from a to b of f of x dx. That's how we find areas. This is the definite integral. A and b simply being your interval, f of x being, well, the f of x, and then we can evaluate. And what's nice about a definite integral is it's related to the indefinite integral. So this is going to be the integral from 0 to 2 of x cubed plus 3 dx. So what I do is I take the antiderivative first and I evaluate it at the interval second. So the antiderivative being, this is going to be x to the fourth over 4. Oh, sorry, that's x squared. Thank goodness. Boom. So, my bad, x squared. So this is going to be x cubed over 3. X cubed over 3 plus 3x. We don't need the plus c because we're going to evaluate it from 0 to 2, which means we're going to plug in 2 first, we'll plug in 0 second, and then we will subtract those values. So this is going to be 2 cubed over 3 plus 3 times 2. That's plugging 2 into here. Now we're going to subtract it, and now we're going to plug 0 into here. So 0 cubed over 3 plus 3 times 0. What you'll notice is you'll get 16/3 right here, and you'll get 6 right here, and this entire thing is going to be equal to 0. So, 16 over 3 plus 6, that's gone. And we know that this is equal to 26/3, which is our answer. So, the previous one was using limits to verify these indefinite integrals. So this is eventually what we go to from now on. You have to do this once. You have to use a Riemann sum once. But eventually it's really we're gonna be doing this for the rest of calculus, calc 2 and calc 3 even. Talk a little bit about Riemann sums. They will help us build this integration techniques. But not a lot of Riemanns after this. Alright, so that is how we find areas. Now what we're going to do is we're going to find some definite integrals and how they relate to areas. Eventually we're going to use the fundamental theorem of calculus part 1. This right here is considered the fundamental theorem of calculus part 2, that the way you evaluate a definite integral is through an antiderivative evaluated at the endpoints of the interval. Alright. So if I give us some values, so given, say, the integral from 2 to 5 of f of x dx is equal to 3, the integral from 5 to 7 of f of x dx is equal to -1, and the integral from 5 to 7 of g of x dx is equal to 8. What I want to do is I want to evaluate the following. So, evaluate. A. What is the integral from 5 to 2 of f of x dx? B. What is the integral of say, 5 to 7 of 4 times f of x dx? C. What is the integral from 5 to 7 of 2 f of x minus 9g of x dx? And we'll talk about these first, so we get a couple more. Alright. Really what these things are showing is these represent areas under curves. So, if I have a function right here, let's just say f of x right now. Let's just call it f of x. Maybe it would be more like this then. Let's call this f of x. Let's say this is 2, and this is 5, and this is 7. So, now this is just one particular possibility here. The reason I've drawn it this way is, what I know is that the integral from 2 to 5 of f of x is equal to 3. And really what that means is that this area here, the integral from 2 to 5, if this is the function f, that area is equal to 3. Now you can also get definite integrals of negative numbers, and what that would mean is, some or maybe all of this, this is equal to -1 because it's below the x-axis, so that's why I get a -1 here. Now it doesn't have to entirely be under it, just means that the cumulative area is going to be negative, and yeah, I'm happy with that. So that's really what we mean by these pictures, and then we just kind of want to see what happens here. So there's rules when it comes to evaluated integrals. So what happens when you switch the limits of integration? Well, what this happens is this is the opposite of the original 2 to 5 of f of x dx. That if you switch the limits of integration, you introduce a negative sign. And I know what this value is. I know what this is. That thing right here is equal to this. So this is going to be negative, and this number is 3, so this is going to be equal to -3. What we can do, the same thing as with derivatives, we can do the antiderivatives or definite integrals, is we can pull out constants. So notice there is no 4f of x here. There's no 4 here, so I can't directly replace this with 3. You have to pull out the 4 first, the integral from 5 to 7 of f of x dx. So what I can see is that now I have this piece here, because there was no 4 there. So you have to pull out the constant first, and now I know that this piece right here is equal to that -1. So this is 4 times -1. So this is going to be -4. Now, very similarly with derivatives and integrals, the integral of the sum or the integral of the difference is going to be the difference of the integrals. So this would be equal to the integral from 5 to 7 of 2 times f of x dx. Minus the integral from 5 to 7 of 9 times g of x dx. And again, I have no 2f of x's and 9g of x's, so what I have to do now is the same thing we did here, is pull out these constants. So this is 2 times the integral from 5 to 7 of f of x dx, minus 9 from the integral from 5 to 7 of g of x dx. And you might ask, do I have to do this, Mr. Van Hamlin? Yes, do the algebra. Show the work. So integral from 5 to 7 of f of x is right here. So this is going to be 2 times -1 minus 9 times integral from 5 to 7 of g of x is going to be 8. So I have minus 2 minus 72, so this is going to be -74. One more I can fit in here, and then we'll do a last example. Say the integral from, I don't know, let's say 3 to 3 of f of x dx. Now remember, this represents the area from this point to this point. So even if I have a function that says like f of x that looks like this, if I'm just going to go from 3 to 3, I'm really asking is what's the area of that, of that infinitely small line. So what we say is this is just equal to 0 because this has 0 width. This is because there is 0 width. It's a 0 width interval. I'm just going from the interval from 3 to 3. So that's why this is equal to 0. Now, one last one would be something that might look like this, e. What about the integral from 2 to 7 of f of x dx? I had the picture over here a second ago. Something that looked like this. So this was 2, this was 5, this was 7. Now I knew that this thing was equal to -3, and this thing right here is equal to -1 as far as our areas are concerned. So what this is called additivity. That the integral from 2 to 7 of f of x dx would be the same thing as the integral from 2 to 5 of f of x dx. It's going to be this piece plus this piece. So if I want to find the interior area from 2 to 7, I have to add the area from 2 to 5 to the area from 5 to 7 of f of x dx. This being equal to 3, plus this being equal to negative 1. So the cumulative area is going to be equal to 2. All right, fundamental theorem of calculus part 1. This really pertains to how derivatives and integrals are kind of inverses of each other. Kind of. Close. So what the theorem says is the derivative with respect to t of the integral from a to x of f of t dt is equal to straight up f of x. Where a is a constant, x is your variable. So that this is the fundamental theorem of calculus, part 1. So what it kind of shows is that the derivative of the integral is equal to the function. So that these two things kind of cancel each other out. The derivatives and integrals kind of cancel each other out. The problem is this is a function of t, and when we're done canceling, this becomes a function of x. So let me show you an example. And we'll do it the long way first and then the short way second, because the long way doesn't always work out. Sometimes you don't know the antiderivative. So let's say evaluate. How do I want to write that? Evaluate or simplify. So let's say I'm going to say use fundamental theorem of calculus to evaluate. Use fundamental theorem of calculus to evaluate. Let's go from the integral from, let's see, the derivative with respect to t of the integral from, I don't say, pi over 2 to x of the cosine of t dt. All right. Let me show you the long way first, and then we're going to abandon that completely because it's a waste of time. This is of this form right here. I don't know if you guys can tell already what the answer is going to be, but it's instant. You know, using this is instant. This is your function of t. This is a constant. This is a variable. So really, boop, boop, done. So let's just kind of cover this up. That I know that if I want to find the antiderivative, this definite integral, I know that this is the derivative of the sine function. So I take the antiderivative of the cosine first. I'm going to write that d dt next. So what I'm doing is I'm working inside the parentheses first. So we're just going to do this part first. So this is going to be the sine of t evaluated from pi over 2 to x. So we just took the antiderivative. And now we have to evaluate the endpoint. So now this is going to be the derivative with respect to t of, we'll plug in the top, this is going to be the sine of x minus the sine of pi over 2. Let's see, pi over 2. The sine is going to be the y-coordinate, so this is 0, 1. So this is just going to be 1. So this is going to be the derivative with respect to t of the sine of x minus 1. Do I want to write that? This is wrong. That's why. My bad. My bad. No wonder I look so funny. That's better. That's better. So the derivative with respect to x of the integral from a to x of f of t dt will be equal to f of x. So now what I'm going to do is I'm going to take the derivative with respect to x of everything. So the derivative with respect to the sine of x is going to be the cosine of x. And the derivative with respect to negative 1 is going to be equal to 0. So this is immediately the cosine of x. And if you guys notice, using that really quick trick, that the integral, the derivative of the integral is going to cancel. And instead of this saying a function of t, it's just going to be this function, this exact same function of x. So instead of this being the cosine of t, this is immediately just going to become the cosine of x. And that's because, you know, these kind of cancel each other out. I did something super messy because maybe if it was upside down, you know, if it was a reciprocal, you could find its antiderivative, but not now. There's no way. So this is a constant, this is a variable, we're good. So what happens is this function of t is just going to turn into a function of x. So everywhere there's a t, now it just becomes x. You know, the derivative of the integral will kind of cancel each other out. So this would be x all over, you know, x cubed minus 3x squared minus 4x plus 1. We're done. Done. Now there's one more tricky one, and that happens when this is not just x. What happens if it's like an x cubed or an x squared? So derivative with respect to x of the integral, say from 1 to x cubed of let's say like does it even have to be that? I'm not even sure if I don't want that one. Okay. So what's going to happen here is these two things are going to cancel each other out. So this is going to go here. Actually, here's kind of a clever one. What if I did this? What if I wrote it that way instead? Well, what you would have to do for this is you'd have to use a previous rule that we did. Is we'd have to go, this is the derivative with respect to x. When you switch those limits of integration, what you're going to do is you're going to introduce a negative sign. That the bottom has to be the constant and the top has to be the variable. So if you ever see them switched, where this is a variable down here and a constant up here, you have to switch them and introduce that negative sign. Okay, now let's back to kind of where we were. So what's going to happen is this is going to go here. This has immediately become the secant. Well, don't forget that negative sign. So it's going to be that negative sign, that secant of x cubed. But we still have to multiply by the derivative of what's inside. This essentially becomes a chain rule. So I still have to multiply by the derivative of this. So this is going to be a 3x squared. And now we're done. So if this is a more complicated thing than just x, you'll still have to multiply by the derivative of that thing. Notice that this was just an x, so multiplied by the derivative of x would just be a 1 here. Let's do a couple definite integrals. So this would be the fundamental theorem of calculus part 2, and then some u substitutions. How do I say that? This is evaluate. Fundamental theorem of calculus. Okay, so if I want to evaluate this, and actually, let's make the bottom one smaller, because sometimes I'll write that in there. Don't get confused if this goes from 3 to 1. It's not a big deal. If you want to switch the limits and introduce a negative sign, you're welcome to, but it doesn't really matter. There's no requirement that this has to be the smaller number and this has to be the bigger number. Just notice that it will be opposite of the integral from 1 to 3. So if you did evaluate the integral from 1 to 3 and evaluate the integral from 3 to 1, they will not share the same sign. So what I know is, using the fundamental theorem of calculus, that I just have to, you first have to take the antiderivative first. So this is going to be x squared minus 5x. And then you have to evaluate it at the endpoint, so from 3 to 1. So when you evaluate this, you're going to plug in the top first. So 1 squared minus 5 times 1 minus, now don't forget it's a binomial, so parentheses, we have 3 squared minus 5 times 3. So that's the fundamental theorem of calculus, that antiderivative first, evaluate second, top minus bottom. So this is going to be equal to 1 minus 5 is going to be negative 4, minus 9 minus 15 is going to be negative 6, minus a negative 6. So this will spit out the answer 2. Again, we have to find the antiderivative first. So what's the antiderivative of 1 over x? Well, what function did I take the derivative of to get a 1 over x? Well, the derivative of the natural log of x is 1 over x. So this is equal to, the natural log of x. That's the antiderivative of this 1 over x. And then I have to evaluate it from 1 to 5. So, top minus bottom, this is going to be the natural log of 5 minus the natural log of 1. The natural log of 1 is equal to 0, so this will be the natural log of 5. Substitution. So I just want to be able to find the antiderivative, and then we'll find a definite integral using subs. So substitution uses the idea that the integral of f of g of x times g prime of x dx will just simplify to the integral of f of u du. But if I have something of this form, I can just rewrite it of this form, and then we can evaluate this really quickly. So the whole idea of this is like u would be equal to your g of x. So you can see that this is just f of u. Now du dx is going to be the derivative of this thing, so this would be equal to g prime of x. So if I just want to simplify the du is going to be g prime of x dx. So that this g prime of x dx becomes du. So how this works, evaluate. What if I have, let's say the integral, the integral of, say 2x times x squared plus 1 to the 5th power dx. So what I have is I have a function that's of this form. Then I have a function stuffed inside of a function. I can see that it's a composite function. There's a composite function here. So the f function being the outside function, the g function being the inside function. So this is your g, this is your f. So your f really is your 5th power. So your f function being that 5th power function. And then your g of x being your x squared plus 1. Now you still have a g prime of x. So what we do is we make a substitution. So what I say is that u is going to be equal to that x squared plus 1, that I've identified the inside function, this piece right here. Now your du, which is just going to be very similar to your derivative, it's considered your differential, but it's your derivative followed by the differential of the same variable. So your du is going to be the derivative of this thing. So this is going to be 2x, followed by dx. So the difference between a differential and a derivative, the derivative is going to have du dx, but the differential is going to have du, sending the dx to the other side, so the dx. So now I can see that this 2x dx right here, this 2x dx, they don't have to be next to each other. Think of multiplication as being commutative. This is the multiplication here. So this is going to be your g prime of x dx. So if you really want to write it this way, I could have rewrote this as, the integral of x squared plus 1 to the 5th times 2x dx, if you'd prefer to see it look just like this. So, this is this piece right here is your f of gx, and this right here is going to be your g prime of x dx. So what it says is I can make these substitutions that, this piece right here, this x squared plus 1 simply is just u, and that this 2x dx is going to be 2x dx is going to be du. So the only thing that's still black here as far as the color is going to be that fifth power. The only thing that remains is this f function. So the only thing that remains, let's say this is going to be blue then, because there's your f function. So the only thing that remains is going to be that f function, which is going to be blue. So this is u to the fifth power, and this thing right here is going to be du. So we have the integral. I have enough colors here. This is going to be the integral of u to the fifth power, because that's your f function, and then your 2x dx is going to be your du. And now what we have is we have a very simple function to take the antiderivative, as opposed to something that's pretty complicated here. So the integral of u to the fifth is going to be equal to u to the sixth over 6 plus c. Now, this is the antiderivative in terms of u. We have to turn it back into in terms of x. So we just unsubstitute. U is just x squared plus 1. So just rewrite this. This is going to be x squared plus 1 to the sixth all over 6 plus c. And we're not expecting you to expand this x squared plus 1. That's a little ridiculous. We're just trying to find an antiderivative. Now, one of my favorite ones that I always put on here, so here's a gimme. I always put this on here. Is going to be, let's say b, what is the antiderivative of the tangent of x dx? I do this because this is a perfect u substitution, but you have to rewrite it first. Because what I need is I need a function. I need this to be really kind of the composition of two functions. And I know that the tangent function is built of two functions. That this is the integral of the sine of x over the cosine of x dx. So your job is to figure out what is the inside function. What function is your g of x? Now, it's almost always your denominator, or it almost always lives in your denominator. The only time it's usually not a denominator is when you see like a natural log. Because the derivative of natural logs give you denominators, that's why. So what we'll notice is that if I make my u equal to the cosine of x, I'm also going to have to find a du as well. So du being, boy, I wish this was a bigger marker. I have a better green one. Oh, yes, anyways. Sweet. So your du being, well, the derivative of the cosine is going to be minus sine of x dx. Notice that this is a numerator here. This is sine of x over 1. So you can't choose sine to be your u and your du to be cosine, because the derivative of sine is cosine, and that's not a cosine on the bottom. So that's why we have to choose the denominator to be your u, because this is a numerator right here. So now we have to make our substitution. So notice that this cosine of x becomes your u, and then this sine of x dx becomes your du. But unfortunately, I have a negative sign. So what I can do over here is this is going to be minus du is going to be equal to the sine of x dx. The sine of x dx becomes negative du. So I'm just going to pull the negative out front, because that's what I can do with constants. So this is going to be, notice what's still, your f function is going to be, what's still black is really what I tell most people, though I wrote it in blue last time. Let's just leave it in black. So that your f function is the function that's really left alone, and your f function is this division. So we still have the division bar. We still have my integral. Now, cosine is on the bottom, it's your u, so that's your u function. And then your du, or your negative du, which means that this has to be a 1 on top. Or I can say that this is negative 1 du if that helps. So now I can find the antiderivative of this, that the integral of 1 over u is going to be the natural log of u. So minus the natural log of u plus c. And don't forget to unsubstitute. U is your cosine of x. So just rewrite that as the cosine of x. So this is minus the natural log of the cosine of x plus c. Now a lot of times I see people pop these things in the AI, and I kind of know that they'll just write the answer as the natural log of the secant. And the reason why it's a secant is you can take, with logarithms, you can take this negative 1 and you can put this to the power. So this would be the natural log of the cosine of x to the negative 1 power. And cosine on the denominator is secant. So you could rewrite this instead of negative natural log of cosine, you could write this as the natural log of the secant plus c. All right, let's say one more. Okay. All right, so in order to find this using substitution, I really just have to figure out my function inside my function, and we can see that, this x cubed minus 5 is likely going to be my u. So u is going to be x cubed minus 5, which means I have to also find my du. So, du is going to be the derivative of this followed by that differential. So 3x squared dx. Notice that I don't have a 3x squared dx. I only have an x squared dx. So what I have to do is I have to algebraically simplify this thing to just become an x squared dx. So I need this to just say x squared dx, which means in order to get rid of a multiplication of 3, I'm just going to divide both sides by 3. So 1/3 du is going to be x squared dx. So now I can make my substitution. Notice that the thing that's still black here, my function is going to be the integral, and my radical is still there. This piece becomes your u. And then your x squared dx, you can say is, if you want to write it here, you can say times 1/3 du. But we almost always just pull out the constant, so instead of saying that, I'm going to say 1/3 the integral of root u du. Just take the constant, put up front. All right, now antiderivatives, we need to use the inverse power rule. So this is going to be 1/3 integral of u to the 1/2 du. So adding 1 to the power and dividing by it. So this is going to be 1/3 u to the 1/2 plus 1 is going to be 3/2 divided by 3/2 plus c. So this is going to be 1/3 divided by 3/2, the same thing as multiplying by 2/3 u to the 3/2 plus c. So this is going to be 2/9 u to the 3/2. Last thing is, don't forget to unsubstitute. That your u is going to be x cubed minus 5. So this is going to be 2/9 times x cubed minus 5 to the 3/2 plus c. All right, last thing we're going to do is substitution with definite integrals. Maybe areas between curves, and then a bit less. So, what if I want to let's do one example. Very, very similar. It really is. If you can do this, you can do substitutions with definite integrals. So maybe I'll do two. Let's say let's go the integral of cosine of x times whatever, say square root of sine of x plus 1 dx. What do I want to go? Let's go from 0 to 1. I know they all have nice limits there. All right, so in order to do this, there's two different approaches you can take. You could really you could find the antiderivative using the original function and then evaluate top minus bottom. Or you can, so let's kind of do that first. I think that's probably maybe the best way to look at it on this video so I don't get you confused. So what we can do is just our u substitution. U is going to be the function inside of the function, so sine of x plus 1. Clearly this is stuffed inside that one. The binomial is kind of the obvious one. So then du is going to be the derivative of the sine of x, which is going to be the cosine of x dx. You know, derivative of 1 is 0. So there's the cosine of x dx. So really, without the limits of integration, this is the integral of, this is root u du. This becomes u and this becomes du. We'll pop the limits of integration back in a minute here. What I want to do is let's find the general antiderivative first, and then we'll evaluate it in a second. So this is going to be equal to the integral of u to the 1/2 du, which is going to be u to the 3/2 divided by 3/2 plus c. So we got 2/3 u to the 3/2 plus c, where, u is this thing. So this is going to be 2/3 times the sine of x plus 1 to the 3/2 plus c. Now, when we're doing definite integrals, we don't need the plus c. We're going to do top minus bottoms. Those c's are going to cancel. So if I want to evaluate, the integral of this from 0 to 1, I'm just going to evaluate the integral, its general antiderivative from 0 to 1. So this is the antiderivative of that thing. So now just evaluate it, use the fundamental theorem of calculus. So that means top minus bottom. This is 2/3 sine of 1 plus 1 to the 3/2. Oh, let's make this a pi. Just to make it easily evaluate. Minus 2/3 sine of 0 plus 1 to the 3/2. All right, sine of pi, we know it's right. There's pi. So sine of pi is going to be the y-coordinate -1, 0. So the sine of pi is going to be 0, so that's going to be gone. So this is going to be 1 to the 3/2, which will just be 1. So this will be 2/3 times 1 to the 3/2, or 2/3 times 1, minus 2/3. The sine of 0 is right here, which also is going to give us the y-coordinate, which is 0. So this is 2/3 times, sine of 0 is 0, so this is going to be 1 to the 3/2, which is also going to be 1. So we're going to have 2/3 minus 2/3, which is going to be equal to 0. That can happen. Now, let me show you a particular picture of why that might be the case. So I know that this function is more complicated than the thing I'm going to draw, but you could possibly have a function that looks like this from 0 to pi. Noting that the area here would give us a positive number and the area here would give us a negative number. Now, if these areas are the same size, then they will annihilate and you'll get a definite integral of 0, which is likely what's happening here. You're going to get something like that that'll cancel each other out. Now, let's do one more. I just want to do a logarithm just so you at least see it with substitution, because that logarithm is kind of a It's one of the ones where you would not expect to use a numerator. You usually try to use denominators when you see rationals for substitutions. So let's say I have something that looks like this. Say the integral from 1 to, let's go like the integral from 1 to e squared of 2 natural log of x all over x dx. So we can see that we have a fraction here, and I said it's almost always the denominator being your u function, but unless you see natural logs, and then they're almost certainly going to be the natural log function is going to be your u. So let me kind of verify this to you. So I'm going to say that the natural log of x is going to be my u, and I'll just kind of show you why that's the case. Remember that we also have to follow it by its, the du, because we can't just substitute x's, we also have to substitute dx's. So your du is going to be the derivative of this thing. Well, the derivative of the natural log of x is 1 over x dx. And notice that that's what we get over here. I get a 1 over x dx. I get something like that, don't I? Now, I don't need a 1 over x dx. What I need is a 2 over x dx. So I'm going to multiply both of these by 2. So 2 du is going to be 2 over x dx. So now that's all my things. This becomes u, and the 2 over x dx becomes my du. What's neat is this is going to be the integral of just u du. Now I noted I dropped the limits of integration. We'll find its antiderivative first, and we'll plug those things in second. Now there's just a 1 up here. It's just u. So the antiderivative of u is going to be u squared over 2 plus c, but we know we're going to do definite integrals, so I'm not going to worry about the c. So where u is going to be the natural log of x. So this is going to be the natural log of x squared, because that's your u. This is your u, all over 2. And I'm going to have to evaluate it at the limit. So this is going to be 1 from e squared. So now, top minus bottom. The natural log of e squared over 2 minus the natural log of 1 squared all over 2. What's nice is natural log and exponential are inverse functions. So this just becomes, the natural log of e squared is just going to be 2. So this will just cancel, just become 2. So this will be 2 squared over 2. And I know the natural log of 1 is equal to 0. So that's just going to be 0 squared over 2. So that's going to be 0. So this is going to be 4 over 2, which is going to be 2 over n. Now, areas between curves and bounded stuff, I probably won't finish it all. I'll just show you how to set this up. So let's talk about trying to find the area of a curve bounded by the x-axis, and then we'll try to find the area bounded by 2 curves. We'll just set this up, and then you can find the antiderivative and then plug them in using what I'm erasing now. So let's see. Okay, so something like this. No, let's say minus 2. I need it to work nicely. If I want to find this, what I know is, I know this is a quadratic equation, and we can factor this. This is x minus 2 times x plus 1. So I can see that, this quadratic is going to look like this. Now what I'm asking for is I'm asking for the area bounded by this quadratic and the x-axis. I'm asking for this area right here. Now sometimes students give it to me as a positive number. Sometimes they give it to me as a negative number. I don't really care. I'm just trying to ask you to find that bounded area. Technically, when you find the antiderivative, it's going to be a negative number. So if you if you write it as the negative number, I'm okay with that because it just happens to be below the x-axis. But if you're like, oh, you asked for the area, you really wanted a positive number, so they give me a positive number, that's fine too. All right, so what I know is I know this is -1 and I know this is 2. So if I want to find that area, the area is going to be the integral from a to b of f of x dx. So this is going to be the integral from -1 to 2 of x squared minus x minus 2 dx. Which means I'm going to have to, take the antiderivative, x cubed over 3 minus x squared over 2 minus 2x evaluated from -1 to 2, which means I'm going to have to plug in, the top. So 2 cubed over 3 minus 2 squared over 2 minus 2 times 2. Subtract when I plug in -1, so -1 cubed over 3 minus -1 squared over 2 minus 2 times -1. And then, simplify that. This will give us, that'll give us our number. So in the interest of time, I'm not evaluating. This is now just plug into it, simplified. So that's how we find that. Now notice that you will get a negative number here because I'm taking the antiderivative from -1 to 2. So you're actually finding this here. So this will spit out a negative number when you're done because it's below the x-axis. Now, if you want to find, say, the area bounded by the curves, okay. So if I want to be able to find the area bounded by these curves, really what I know is I have a quadratic and I have a linear. I have something that probably looks something like, something like this, let's say. Well, it's a negative slope, so something more like this. So what I'm trying to do is I'm trying to find this, this set bounded area. So in order to do that, I'm going to need these intersection points. So I need to know what this is, and I need to know what this is. So in order to do that, let's find the intersections by setting these things equal to each other. So x squared minus 3x minus 1 is equal to minus 2x plus 5. So adding this is x squared. Adding 2x is going to be minus 1. Subtracting 5 is going to be minus 6 is equal to 0. And this thing factors to x minus 3 times x plus 2. So I can see that this is going to be 3, and this is going to be negative 2. So what we know is the area by bounded curves is going to be the integral from a to b of f of x minus g of x dx. And this is where f of x is the bigger function. So where, f of x is greater than or equal to g of x. Now this being the quadratic function open up and this being the linear function open down, it's got to look like this. So the bigger function is going to be that linear function. The smaller function is going to be this quadratic function. So we just have to subtract these two things. So this is going to be the integral from, minus 2 to 3. We go from left to right, minus 2 to 3 of f of x, which is going to be x. Nope, f of x is the bigger function, my bad. I should probably have wrote these as y's, just so we don't claim f and g's immediately. So this is your g and this will be your f because this is the bigger function. So this is going to be minus 2x plus 5 minus x squared minus 3x minus 1 dx. And now we just, we simplify this thing. Minus 2 of, this is going to be minus x squared plus x plus 6 dx. And then again, this is the definite integral of a polynomial, so minus x cubed over 3 plus x squared over 2 plus 6x, evaluated from minus 2 to 3, plug in top minus bottom, minus 3 cubed over 3 plus 3 squared over 2 plus 6 times 3, minus, when you plug in the bottom, this is going to be minus 2 cubed over 3 plus minus 2 squared over 2 plus 6 times minus 2. So that's what that'll be equal to. Simplify, you get your answer back. This will give you a positive number because you're doing a bigger function minus smaller function. And that's it. So hopefully this will help you on your test. I know it's 2 hours long, but it is what it is.